We've now been introduced to integration, which lets us find the area of a shape by essentially splitting it into infinitely many tiny parts and then smoothly summing up those parts. In this lesson, we're going to try to get a better understanding of integration by taking properties of how we intuitively feel like it should work, and then seeing how far we can push those properties. Imagine you've just gotten a brand new 3D printer, and you've started making all sorts of cool things with it. It's a lot of fun. One day, the entrepreneur in you gets an interesting idea. Maybe you could start selling some of your creations online. So you decide to start a small business. You start keeping track of your daily revenue, how much you bring in from the stuff you sell. But of course, you also have costs. The cost of your materials, fees from your online portal, and so on. So you keep track of those too. At the end of each day, your profit is the difference between revenue and cost. How much money you made minus how much you had to spend. Sometimes that profit will be positive when you make more than you spend, but other times it'll be negative when you have to spend more than you make. It happens. Now, at the end of the month, what's the total amount of profit you've managed to accumulate? There are actually two ways you could find out. On one hand, you could calculate your profit for each day individually, daily revenue minus daily costs, and then sum all of those individual pieces together. Alternatively, you could separately sum up your total revenue for the month and your total costs for the month, and then subtract those two totals. Now, technically, when we're talking about daily revenue, costs, and profit, that's discrete. So you might argue that we don't really need an integral here. But we could just as easily keep track of how much we make and spend on a much more granular level, say down to the second if we want. I bet your credit card company does exactly that. So it's still useful to think of this in terms of integration. Now, whenever there are two different ways of answering the same question in math, that's a hint that there's a general principle under the hood. In this case, it suggests how we might find the integral of a sum, or in our case, a difference, of two functions. Just find the sum or difference of the individual integrals. By the way, this should remind you of a similar rule we found for derivatives earlier on. That's not a coincidence, and you'll see why pretty soon. There's also a similar rule for integrating a constant multiple of a function. Just get the constant multiple of that integral and you're done. See if you can think of a real-world situation that demonstrates that property. So now we've got a couple of ways of analyzing integrals based on what's in the integrand. That's what we call the function that's getting integrated. It's nice to have a word for it so we don't have to keep saying the function you're integrating every single time. But things really get interesting when we start to toy around with the limits of integration, the numbers specifying the left and right endpoints of the interval. Up to this point, we've always assumed that the lesser number goes on bottom and the greater number goes on top. And that's made sense given our real-world contexts. We're looking for how much stuff, such as money, or for that matter, bathwater, gradually accumulates between some starting time and some ending time. In fact, the 3D printer actually gives us a pretty good analogy. Our area builds up gradually from the start to the end, kind of like how the printer builds up whatever we're making, bit by bit, layer by layer, starting from the bottom to the top. So when you think of integration, it's often a good idea to think of the area doing this as well, starting at the left and then slowly building up from left to right. But do we really have to always think of this as a hard and fast rule? Or might it be useful to relax this requirement once in a while? Maybe, but we'd have to figure out how to interpret it first. Math is full of instances where we have to push the limits of our understanding. When you first learn about numbers, they're just simple counting numbers that can tell you how many apples there are in front of you. But then you learn about negative numbers, fractions, irrational numbers, even imaginary numbers. Each one requires you to rethink what number really means in order to fit those new things into the mental framework of what you already know. One of my favorite examples of this is what happens with exponents. When you first learn them, exponents stand for repeated multiplication. 4 to the third power means 3 copies of 4, all multiplied together. Pretty simple. But what if we want to, say, raise 4 to the 0 power? If we have no copies of 4 to multiply together, is that maybe just 0? This defies the original concept of exponent. So how can we make sense of it? Well, one way is to find some fundamental property of exponents that we think should always be true, and then use that property to discover what happens in those weirder situations. In this case, we might decide to hold on to the fact that when we collect together different powers of a base, we add the exponents, since that's the total number of copies we're multiplying together in the end. In algebraic language, we would say that x to the a times x to the b equals x to the quantity a plus b. So let's use this equation to go back to our original question about 4 to the 0. We'll let x be 4, and then we'll let b be 0. So we have 4 to the a times 4 to the 0 equals 4 to the quantity a plus 0. But a plus 0 is just a, so that right side is really just 4 to the a again. So what can you multiply by 4 to the a and still get 4 to the a back? The only number that fits is 1. And that works no matter what base we're using. There's nothing special about 4 here. So any number to the 0 has to be 1. Not because of a rule your textbook or your teacher told you, but because that's what's consistent with how we intuitively feel like exponents should work. Using similar logic, we can discover that negative powers give us fractions and fractional powers give us roots. It doesn't make sense to multiply negative or fractional copies of a base, but that doesn't matter. Our equation lets us discover how to extend what exponents mean and apply them to new situations. Mathematicians call this a functional equation, which is just an equation that describes how some function should work. So with that example in mind, let's see if we can find a similar relationship to latch onto with integration. In fact, you might have thought of it already. Let's go back to our business example. Suppose over your first month in business, your net profit is a total of negative $1,000. That is, you had to spend $1,000 more than you brought in. But then business starts picking up, and over the second month in business, the net profit is positive $3,000. You made $3,000 more than you spent. So what was your net profit over the first 2 months? Well, you just add them together. Negative $1,000 plus positive $3,000 equals positive $2,000. So now you have $2,000 more than when you started your business 2 months ago. What we've just demonstrated is called the additive interval property. If we integrate a function from a to b, and then further integrate it from b to c, then the sum of those two integrals should just be the whole integral from a all the way to c. In fact, it's actually a lot like what happens when we combine exponents. When you collect some stuff, and then collect some more stuff, you can add up all the stuff you've collected. That just makes sense. Alright, let's start playing around with this new additive interval property and see what new properties we can uncover. Integral from a to b plus integral from b to c equals integral from a to c. Okay, what if we take c and replace it with b? So now we'd have integral from a to b plus integral from b to b equals integral from a to b again. It's unchanged. that means the integral from b to b has to be 0. And that's what we call the zero interval property. If the endpoints of our interval are the same, then the integral has to be 0. And if you think about it, that makes a lot of sense. If there's no interval to integrate over, then we won't manage to accumulate any area. Put back in the context of our business example, if we generate, say, a report where the start and end time are exactly the same, such as Friday the 7th at 11 a.m., then there won't be any profits in the report because there's no time for them to happen in. Okay, let's go back to our equation. What if we take c and dial it back even further, replacing it with a? So now we've got the integral from a to b plus the integral from b to a is the integral from a to a. Okay, based on the last problem, we know what to do with that now. That right side is equal to 0. So that means that the integral from b to a has to be the opposite of the integral from a to b. It has the same absolute value, but it's the opposite sign. So we'll call this the backwards interval property. The integral from b to a is the opposite of the integral from a to b. That might seem a little weird, but think of it this way. Remember how our profit over the first month was negative $1,000? Well, if we started out at the end of the month and rolled the clock back, so to speak, then you could imagine we'd gain $1,000 as we go back to the beginning of the month, say, to figure out what we might have done differently. So reversing the interval sort of lets us go back in time. Okay, we found a bunch of neat properties of integrals now. Some let us manipulate our integrand in certain ways, and others let us manipulate the limits of integration. Now, you could find these in any textbook, or I certainly could have given them to you as just a rule to memorize, but it's so much more satisfying to discover for yourself why they have to be true. I may be preaching to the choir here, but I think it's worth mentioning that you should always try to strive for this kind of understanding in a math class. Don't just settle for memorizing rules without reasons, but always try to internalize the why behind them. And always be on the lookout for how you can adapt what you know to new and unfamiliar situations. That's a useful skill, not only in entrepreneurship, but also in mathematics.